Let's talk a little bit more about gravity. If I ask you what the force of gravity is, you would say the force of gravity is mg. The weight of an object is its mass times the acceleration of gravity. Well, that's true on the surface of the Earth, but it's not true anywhere else. If you take your scale to the moon, you'll get a very different reading for your weight than you will on the surface of the Earth. So we want to know what's the universal law of gravity. Not just an object at the surface of the Earth interacting with the Earth. That's what this formula is. M times G. An object on the surface of the Earth interacting with the Earth. But what if I want to know any two objects? Two objects interacting with each other out in space. An object interacting with the moon. An object interacting with Mars. Any two objects, anywhere, I need a universal law of gravity. And what might a universal gravitational force depend on? What would influence the gravitational force? It would probably depend on the mass of an object. And it might depend on the mass of the object it's interacting with. And it might depend on how close they are together. But it will be inversely proportional to the distance, because the closer they are, the stronger the interaction will be, and the farther apart they are, the weaker the interaction would be. But actually, it's not just inversely proportional to the distance, it's a 1 over r squared relationship. A lot of things in physics follow this 1 over r squared relationship, inverse square law. And the reason is that things spread out spherically. So let's take a light bulb, for example. I turn on my light bulb, and light energy comes out in all directions, spherically symmetric, in all directions coming out. So if I have a point a certain distance away, and I measure the intensity of the light there, how much light is hitting a certain area, and then I go twice as far away, well, that light has spread out over a much bigger area. The surface area is much bigger, but the same amount of light now has to spread out and cover a bigger surface area. And surface area of a sphere is 4 pi r squared. So surface area of a sphere increases as r squared, so our intensity drops off as 1 over r squared. It's being diluted by this extra area it has to get spread over. Lots of things in physics do that. Gravity is one of them. And so when I put this together, I say the force of gravity is proportional to m1. It's proportional to m2, which means it equals m1 times m2. It's inversely proportional to r squared, the distance between m1 and m2. And I don't want a proportionality, I want to have an equal sign here, so I need some kind of a constant, a proportionality constant. We call that capital G, the universal gravitation constant. And this is our universal law of gravity. Any two masses, m1, m2, and the distance between them r. Now, you might be thinking that if this equation, this universal equation, works for any two masses, anywhere in the universe, then it should work for a mass sitting on the surface of the Earth and the Earth. So if m1 is a mass sitting on the surface of the Earth and m2 is the Earth, what would r be? The distance between their centers? It would be the radius of the Earth. And that should give us the force of gravity on the surface of the Earth. It shouldn't matter which equation we use. One of these equations only works between an object and the Earth when that object is sitting at the surface of the Earth. The other one works for any two objects, any place. So when the object is sitting on the surface of the Earth, they should agree. So lowercase m is the mass of our object. It's sitting on the surface of the Earth. Capital M sub Earth is the mass of the Earth. Capital R sub Earth is the radius of the Earth. Let's figure out what g is. Well, we have to know what our universal gravitational constant is, capital G. You can look that up in any textbook. And it's a very, very small number because the gravitational force is a very weak force. So this is a very small number, capital G, 6.67 times 10 to the minus 11 in our SI units. So we plug this in. The mass of the Earth we know is very large, 10 to the 24th kilograms. The radius of the Earth, 10 to the 6th meters. We plug all this in and we solve for the acceleration of gravity and we get 9.8 meters per second squared on the surface of the Earth. That means that if I ask you what the acceleration of gravity is on the surface of the Moon or on the surface of Mars, you should be able to figure that out. The gravitational force is the only force we have this quarter that can reach in from a distance and exert a force on something. Everything else, there has to be some physical contact for friction, for a normal force. There has to be physical contact for all of our other forces. The only one that can reach in from a distance and exert a force on something else is gravity. And we have to be able to wrap our minds around that. We want to have a model that helps us picture how that can be. And our model is that there's a gravitational field that exists. So what we say is that a massive object fills the space around it with a gravitational field. And any other object with mass that's in that gravitational field interacts with the field, and it feels a force because of that interaction. And what direction do our gravitational field lines point from this massive object? They point in the direction that another massive object would go if we put it there. If I put a mass here, what direction would it go? It would feel a force in this direction, and it would move in that direction. If I put my mass over here, where I showed it originally, it would go in this direction. And so my field line points toward the big mass. So to put my field lines in, I'd put my arrows pointing toward the mass that's producing those gravitational field lines. So this is our model. A massive object fills the space around it with a gravitational field. Any other object with mass interacts with that field, and it feels a force because of that interaction. This is a model. It doesn't have to be correct if it helps us, right? Sometimes models are helpful even if they're not correct. So this is a way that we can picture what's going on, because it's hard to imagine objects exerting forces on each other without touching each other. And we use the same model with electric charges and how they interact and electric forces. We say electric charges fill the space around them with an electric field. And any other object with electric charge interacts with that field, and it feels a force because of that interaction.